the interest of trying to reduce the number of popped fuses in meters, I figure a good starting point for thinking about how to measure voltage and current is to think very carefully about what prepositions the two nouns take. And whenever we get to this point, I always encourage people to just literally repeat the mantra, voltage across, current through, at least 10 times before going to bed each night for about a week. So, voltage across, current through, voltage across, current through, voltage across, current through. Fight, team, fight. Now, why do I encourage this? The idea here is that while it is certainly possible to have ideas for which we don't have vocabulary, it can be a little hard to have ideas for which we don't have vocabulary. And so what I very much want you to do is to, whenever you see the word voltage, to remember that it always can take the preposition across. Any other way of writing a sentence that uses potential or voltage in it, if it uses a preposition, that preposition can always be turned into across, and that is the preposition that I strongly urge you to use. Similarly with current, the preposition that I want you to always take with current is through. This is because voltages are measured across things and currents are measured through things. The best example I can think of here for a fluid flow analog would be to say, think about the flow of natural gas. If you see natural gas going into a building, when it passes through a meter, what they actually have to do is they have to cut the pipe and insert the gas meter as a chunk of pipe. And it literally measures each and every bit of natural gas that passes through the meter on its way. So that's measuring a natural gas current, although usually it just quotes the total amount going through, but you could get a current from it by dividing by the time. It measures a natural gas current, and that is done through the meter. Voltage, on the other hand, can only ever be measured as differences, and it's measured across 2 points. So again, with the fluid flow analogy, this would be like measuring a pressure head, the difference in pressure between one point and another point in a system that you're looking at. So you have to look at 2 places at once, and you measure the difference. So in this photo here, I'm showing you a digital multimeter that has been configured as a voltmeter, and we are measuring the electric potential difference across a battery. So what's called the terminal voltage of the battery. You can see that there is a lead color-coded red and a lead color-coded black, and they are plugged into corresponding color-coded places on the meter. What the meter is quoting is the difference in electric potential between the red lead and the black lead. Now, the value of the potential could be anything, all at both of those points. The only thing that the meter can do is tell you that the red lead is at a potential that is 1.517 volts greater than the potential at the black lead. Remember, we're always free to choose where our zero of potential is. Now, in electric circuits, since meters always measure red lead minus black lead, it's convenient to just say, well, if I put the black lead at the negative terminal of the battery, that would be the lowest voltage point in the circuit. And so if I call that 0, then when I touch the red lead anywhere else, it'll always be a positive number. So by typical convention is to say that 0 volts corresponds to the negative terminal of the battery. And then, like I say, that way you can just leave the black lead attached to the negative terminal of the battery. You can move the red lead around the circuit, and you can read potentials at the different points in the circuit. That is one way that people certainly do this. So in schematic symbols here, what this circuit that we just looked at would look like would be something like this. So you would have your battery, there we go. So you would have your battery. So remember, the long line is the positive terminal, the short line is the negative terminal. And then here, what we're doing is we are just hooking up our voltmeter. The symbol for voltmeter is just a V with inside a circle. We are hooking up our voltmeter across it. So this point right here corresponds with where we touched the red lead to the battery. And this point here will correspond to where we touched the black lead to the battery. And again, what the meter does is it just measures the difference of red lead minus black lead, and it quotes the terminal voltage of the battery as 1.517 volts. Now, typical voltmeters, in order to work well, have very high resistances. So it'll turn out that almost no current passes through. This is like on the level of giga-ohms in typical devices. So almost no current is drawn. Because if you take 1.5 volts and you divide it by a billion ohms, that's less than a billionth of an amp. So this gives us a pretty good sense that when we were reading the number on the display, it was telling us that the EMF of the battery is 1.517 volts. Now, when we actually hook a battery up to load, the number on the meter will drop, we'll see. And this is because as charges actually flow through the battery, the ions going through the battery will be colliding with other chemical molecules in the battery. That creates some resistance. And so it turns out that some work has to be done just plain to move the charges within the battery. And so that will lessen the terminal voltage. But we'll get to that point. So the next photo I want to show you here is of a digital multimeter that has been configured to act as an ammeter. Now, in this picture here, you can see I had to stack two batteries together. So we have a terminal voltage of a little over 3 volts, or around 3 volts. And I've hooked up the red lead to go into the red lead of the ammeter, and then out the black lead coming out of the meter, then goes to the light bulb, and then out from the other side of the light bulb back to the battery. In this case here, the meter is configured to read the current in milliamps. And so what you are seeing here is that 61.3 milliamps are passing through the meter. Now, because there's no place for the charge to leak out, That means that there's 61.3 milliamps passing through the light bulb and 61.3 milliamps passing through each of the batteries. So the way we would draw a schematic diagram for the picture that we just looked at here, you could either draw 2 batteries in series like I just did here, or you could just draw one and then label it 3 volts. That's fine too. And then what I've got here is it's going into the ammeter. And then the symbol for a light bulb is a little loop-de-loop with a circle around it. And the ammeter symbol is A with a circle around it. And then when we get from the other side of the battery, the other side of the light bulb, it returns back to the negative terminal of the battery. So you can see the current, the conventional current, which is the opposite of how the electrons actually flow, is going around the circuit counterclockwise. Actually, let's make that a different color. So it's going around the circuit counterclockwise, passing through every element, including the battery. And the meter was reading that current was 61.3 milliamps, so that would be 0.0613 amps. Now, in order for an ammeter to do its job well, it should have very low resistance. This is because if the resistance were high, then we would see that we would need to have a substantial potential difference across the ammeter. And then that would reduce the potential difference across the light bulb, and then we wouldn't be getting a true picture of the current flowing through the light bulb and the batteries, which is what we care about. So again, in typical devices, this is down to about the level of 1/10 of an ohm or something like that. It tends to be very low indeed. So when you're thinking about wiring these things up conceptually, you can just imagine that the ammeter acts like a wire, especially if it's a digital ammeter. Analog ones, they're not quite as good, but the digital ones are quite good. Okay, so in this last picture here, we've got our battery. We still have our batteries hooked running through the ammeter and the light bulb. But now you'll notice that I have put in a couple of additional leads, and that those leads are going to a voltmeter. So the voltmeter is measuring the potential difference across the battery pack. It measures red lead minus black lead. The red lead is at the red terminal hooked to the left side of the left battery. And the black lead is at the black terminal on the right side of the right battery. And it measures that the voltage difference, red minus black, is 2.73 volts. And here we're seeing that the current flowing through the ammeter, which will also be flowing through the batteries and the light bulb, is 66.9 milliamps. So for this picture here, if we were to draw a schematic for it, that will look like this. So again, we will have our battery, our pair of batteries. I'll just go ahead and draw them as battery pair again, although usually most of the time people just draw one battery and write 3 volts over it. So there's our battery pair. It is again going through the ammeter, through the light bulb and returning back home. And then, here, let me slide this down. There we go. And then, in addition to that, we are measuring the voltage across the battery. So again, what we've got here is this is the red lead of the voltmeter, and over here this is the black lead of the voltmeter, and the display will read red minus black, which in this case is 2.73 volts. Now we are also measuring the current that goes through the ammeter and through the light bulb and back through the battery pack, and that was measured to be 66.9 milliamps here. So now, because there's a junction here, a very tiny amount of current will split off and go through the voltmeter, and then we reconnect here. But this is very tiny. And we can neglect that. And that's because the resistance of the voltmeter is so high. So now I want you to do a very important thought exercise. And even if you don't normally do the pause the video moments when we get to the pause the video, I really do want you to do the pause the video here. So let's say that when you were wiring this up, you accidentally configured both meters to be ammeters. What would happen? Pause and get back with me on that. Okay, so what would happen in this case is nothing good. Because what would happen is if this were actually an ammeter here, its resistance would be incredibly low. Because its resistance would be incredibly low, the current would very much prefer to run through the meter rather than go through the circuit, which has a much higher resistance. In fact, we'll calculate the resistance of the light bulb shortly. So because basically all the current will be flowing through here and the resistance is incredibly low, by twinkle twinkle little star, delta V equals I times R, you know, if you're talking like 3 volts here and this is 1/10 of an ohm, you're talking about trying to pull 30 amps through this meter, you will fry all the electronics in there. Now, the manufacturers of meters are aware that this is a risk, and so most manufacturers will put a fuse into the meter just in case you accidentally miswire it, but you will pop the fuse. And let me tell you, in some brands of meters, that fuse is a royal pain to get to. In older style analog meters, if you have to use one of those, it could swing the needle so hard that you actually snap the needle. So it's double plus ungood if you accidentally configure a voltmeter as an ammeter. Now let's look at what happens if instead of you accidentally configuring both of those meters as ammeters, you configured both of those meters as voltmeters. Again, I want you to pause the video and get back with me on that. Okay, so here the consequences would be less dire. If this were accidentally configured as a voltmeter, you would have made its resistance incredibly high, on the order of a gigaohm. So effectively, this would have become a break in the circuit, and no current would flow through. So the light bulb wouldn't light up. You would just be reading zeros on the meters, sorry, here for this one you would be reading the battery EMF. Here you would be reading 0 because since you're pulling basically no current, the voltage the difference in potential between this chunk of circuit here and that chunk of circuit there will be way below the resolution of the meter to read. So this meter would end up reading zeros and this light bulb wouldn't light. That's a lot less dire than the other case where if you accidentally configure your meters as both of your meters as ammeters, where you would then pop the fuse in this ammeter. So always be very careful, and if you remember that voltages are measured across things and currents are measured through things, that will be a very good guiding star to minimizing the number of fuses that you pop, hopefully keeping it down to 0. Now I did promise we would figure out the resistance of the light bulb. Keep in mind the interconnecting wires all have resistances on the order of about 1/10 of an ohm or so. So it's not going to contribute a whole heck of a lot to the resistance that we're measuring here. But we can figure out the resistance of the light bulb using our good old mantra, twinkle, twinkle, little star, delta V equals I times R. So the resistance will be the voltage that we measured, because not only because this is the voltage across not just the battery here, but it's also basically across the light bulb. Because remember, we can treat an ammeter as if it were a wire. So this is the same difference as if I attached the black lead to this bit of light bulb here and the red lead to this bit of light bulb here. So it'll be the ratio of the voltage to the current. So that will be 2.73 volts. Now we have to take our milliamps and turn them into amps. So it'll be 0.0669 amps. And we get that the resistance of our light bulb is about 40.8 ohms. Now, it is 40.8 ohms when 66.9 milliamps are passing through it. Light bulbs are notoriously non-ohmic devices, and so the resistance will go up as you increase the current passing through it. Alrighty, so in the next video we will take a look at resistance, resistivity, conductivity, and go on from there. Have a good one.